Hello. In the last lesson, we talked in general about energy. In this lesson, we will talk about a specific type of energy, that is heat energy. In order to build the lesson on heat energy, let's start with a brief description of the three states of matter, namely solids, liquids, and gases. Now, what is the difference between these three distinct states of matter? In solids, well, you know that all materials are made of fundamental particles, or the smallest part of a material is called the molecule of that material. Now, in a solid, the molecules are fixed to their positions. Now, they are held together by strong molecular forces. In fact, in the making of a solid like this, the molecules are packed very close to each other, and each molecule is attached to the other molecules with spring-like structures. That means these molecules can vibrate. They can vibrate about their position. Now look at this illustration here. This is an illustration of how the molecules will look in a solid. They are packed very close to each other, but each molecule can vibrate. They can vibrate about their equilibrium position. Now, they vibrate about their mean position. What does a mean position mean? If this is where we place it, then it can vibrate left and right about the mean position. That means they go equal distance to the left and right from their central position. Now that means they have kinetic energy of vibration. Anything that vibrates has kinetic energy. I'm sure you understand what the meaning of kinetic energy is. Kinetic energy is energy of motion. Now, what happens when you supply heat to a solid? When you supply heat, heat is a form of energy. So if you supply heat to a solid, these molecules will start vibrating faster. Now, let me see if I can show you an illustration of that. Now, solids keep their shape unless they are broken. Is that right? A solid has a specific shape unless you break it into pieces, of course. Now, why do they have specific shape? Because the molecules are not allowed to move from their respective places. The molecules are fixed to their relative positions, and therefore a solid keeps a specific shape. A solid cannot be compressed. In other words, because the molecules are packed well within inside, you cannot apply force and make it smaller. You cannot compress a solid. Those are some of the properties of a solid. Now, if you supply heat to a solid, look at this. These molecules are now more agitated. What does that mean? They have more energy. Now remember, each molecule is held to the other. We call it the intermolecular forces. Each molecule is held on to the other by forces. So when they vibrate faster and faster, this force that is holding the molecules together is becoming weaker. That means if you keep on supplying heat to a solid, the molecules will vibrate faster with larger and larger amplitude. A time will come they will break loose from each other, and that will be then a liquid. So as the molecules gain more energy, when you heat a solid, when you supply a solid with more heat, each molecule will gain more energy, and they tend to break away from each other. The force holding them together, that is the intermolecular forces, will eventually break down and they will move away from each other. Solid then turns into a liquid. So as the molecules break away from each other, they gain potential energy. Now you remember I told you in the last class, if an object is on the ground, its potential energy is the least. If I move an object away from the ground, its potential energy increases. In the same way, when two molecules are close to each other, let me see if I can show that to you. If these two molecules are very close to each other, their potential energy is a minimum. When they move away from each other, they gain potential energy. Now, where did the extra energy come from? The extra energy, in order to separate them, in order to separate these molecules that are held together like this, you need to supply extra energy. That is in the form of heat. So when you supply heat, molecules that are held on to each other, where the potential energy is a minimum, they now move away, gaining potential energy. So what happens is, the heat energy you supply at that time become potential energy of the molecules. Well, that's what this statement means. As the molecules break away from each other, they gain potential energy and the solid becomes a liquid. So molecules have more potential energy in a liquid than they have in a solid. Why? Because their distances is slightly greater in liquids than in solids. As the distance between two objects increases, the potential energy increases. Now this is what happens in a liquid. In a liquid, the molecules are no longer bound to each other. They can move about, but they cannot leave the liquid body very easily. You can see they are within the liquid body. They can move about, and that's the reason why a liquid can flow. A solid cannot flow because molecules are fixed to their relative positions. Whereas in a liquid, the molecules are no longer fixed to their positions. The molecules can move about. They have now more potential energy. They can move about. That means the liquid can flow. And liquids do not keep their shape. Why not? Because the molecules are not fixed to their positions. So a liquid will take the shape of a container, whatever container holds it. A liquid cannot be compressed. Again, because the molecules are so close to each other, you cannot compress a liquid. So a liquid cannot be compressed. It will keep the same volume. Molecules are free to move within the body of the liquid. As the molecules in a liquid gains more energy. Tell me, what happens if you now supply more heat to these molecules? Now, in the liquid also, there is considerable intermolecular forces. In other words, there are forces still holding the molecules together. If you supply more heat, now molecules are going to really go away from each other. They gain more potential energy. So as you supply more heat, the molecules in the liquid gains more energy. More energy means they start moving faster and faster. A time will come they would want to move completely away from each other. That means they will gain potential energy by breaking away from each other. Alright? Now, there is very little forces between molecules in a gas. So, when you supply heat to a liquid, the molecules will have greater energy, and a time will come when the molecules will simply break away and get out of the liquid state. And then you have a vapor or a gas. And in a gas, these molecules are virtually free. They are not bound together anymore. In solid, they are very highly bound to each other. In liquids, they are not as much as in solid, but still they are bound to each other. But when they get out of the liquid state, they are not bound at all. They are completely free. There are no intermolecular forces. There is very little force between molecules in a gas. In a gas, molecules are completely free to move about. Now, this is what happens in a gas. You can see they are not attached to each other at all. There's a lot of space between molecules. They can move about at random, and they are completely free. And I have another illustration here of a gas molecule. A gas molecule is in a state of random motion. It is not bound to any other molecules. Alright, now look at the way evaporation, or when a liquid boils, it becomes a vapor. Now the vapor is completely free to move about. A gas can be compressed, and they take the volume of the container they are in. So this is a simple discussion on the differences between solids, liquids, and gases. Let's now talk about heat and internal energy. Now, what is the difference between heat and internal energy? Now, heat is a form of energy, and when heat is supplied to an object, it increases the internal energy of the object. Now, what kind of energy an object has, that can be called internal energy. Now remember, each molecule, as they vibrate or simply move about, they have motion energy. And motion energy we call kinetic energy. And also, when you supply heat, we said molecules can break away from each other, gaining potential energy. So, when we talk about the internal energy of an object, the internal energy is made up of the kinetic and potential energies of the molecules of the object. That is what internal energy is. So, internal energy of an object is made up of the kinetic and potential energies of its atoms and molecules. Atoms and molecules have kinetic energy because of their vibration, sometimes rotation, or translational motion. What is translational? Translate means to move from one place to another. In a liquid, there is translational motion. Molecules move from one place to another. In a gas also, there is translational motion. So kinetic energy of a molecule can be due to their vibrational motion, vibrating back and forth, can be rotational motion, or translational motion. Now, potential energy of atoms and molecules are associated with their relative states or positions. Now, we said when a solid changes into a liquid, the potential energy of its molecules increases. Why? Because a solid changes into a liquid when the forces between molecules decreases. Molecules move away from each other. That means they gain potential energy. When a liquid becomes a vapor, the same thing happens. The molecules break away completely from each other. They gain potential energy. So, when a solid changes into a liquid, the molecules gain potential energy. When a liquid changes into a vapor, molecules gain potential energy. Now, if you trace it back, what will then happen when a gas, when a vapor condenses to a liquid? When a vapor condenses to a liquid, the energy, the extra energy is given off because the potential energy that the molecules have. Now, in order to produce condensation, you need to bring the molecules together. That means the extra energy now is going to be given out. So, when a vapor condenses to a liquid, it gives off energy. When a liquid becomes a vapor, the energy is absorbed to give molecules potential energy. And when a vapor becomes a liquid, that potential energy is given off. In the same way, when a solid becomes a liquid, the potential energy of the molecules increases. That means extra energy is absorbed. When a liquid freezes to become a solid, the potential energy of the molecules decreases. That means heat is given off. Well, we will talk about that as we move on. The potential energy of a system is greater when the objects are farther apart. We talked about that. Now, here I have an illustration. You have an object that is exploding into many pieces. Now, when the object is in one piece, its potential energy is least. And when you break it into many pieces, these pieces will fly away. Each will carry away more energy. That means the potential energy is greater when the pieces are farther apart. Alright, let's now talk about temperature. Now, very often, these terms are not well understood. Now, what is the difference between heat and temperature? Well, we talked about heat. Heat is a measure of the internal energy of a substance. And internal energy is made up of the kinetic and potential energies of the molecules of that substance. Well, what is temperature? When heat is supplied to an object, you know its temperature increases. So, let's talk about that. What is actually temperature? When heat energy is supplied to an object, its temperature rises. Now, the rise in temperature is purely due to, I want you to keep attention to this one. The rise in temperature is purely due to the translational kinetic energy of the molecules of the object. In other words, the increase in potential energy has nothing to do with temperature. An increase in temperature is caused by an increase in kinetic energy only. Alright. Now, let's see if I can show you a relation between heat and temperature. Now, here I have an illustration of a certain amount of gas enclosed inside a container, and you can see the gas molecules are in a continuous state of motion. And the speed of motion is what determines the temperature. This is a lower temperature. What happens when you increase the temperature of the gas? When you increase the temperature of the gas, the molecules will speed up. Their kinetic energy will increase. So, temperature depends on the kinetic energy of the molecules of the substance. Now here, this shows a little higher temperature. The molecules are moving faster now, showing that the temperature is higher. So, temperature is a measure of the kinetic energy of the molecules of a substance. Okay. Now watch this illustration. I have two beakers, one a big beaker and the other a small beaker, and I'm going to supply the same amount of heat. I'm going to supply the same amount of heat to both. Alright? If the same quantity of heat is supplied to different quantities of water, the increase in temperature will not be the same. Is that right? If I keep thermometers in both these, I'm supplying the same quantity of heat to the amount of water in the small beaker and also the amount of water in the big beaker. Now, which of these two will show a greater increase in temperature? Well, obviously, the small beaker will show a greater increase in temperature. Why? Because the amount of heat you supplied in the small beaker is shared among small number of molecules, and the amount of heat supplied to the big beaker is shared among large number of molecules. That means the increase in energy per molecule, the increase in energy per molecule will be greater in the small beaker than in the big beaker. And therefore, we can therefore say kinetic energy is actually a measure of temperature of a substance is actually a measure of the kinetic energy per molecule. You see, we supply the same quantity of heat to both these beakers of water. The temperature of the water in the small beaker is higher. Now, why did that become higher? Because the amount of heat received by each molecule in the small beaker is higher than the amount of heat received by each molecule in the big one. I hope that is clear. Now, if I give a big packet of chocolate to a group of 10 students and the same packet to a group of 100 students, where will the number of chocolate per students be greater? In the smaller group. In the same way, the amount of heat gained by each molecule in the smaller beaker is greater. That means the increase in kinetic energy per molecule is greater in the small beaker than in the big beaker. That tells us that temperature of an object is a measure of the average kinetic energy per molecule, whereas the internal energy or heat is a measure of the total energy of all the molecules, that is kinetic and potential. So try and distinguish between temperature and heat. I will say that again. Temperature is a measure of the average kinetic energy of a molecule, whereas the internal energy is a measure of the total energy of all the molecules, which can be kinetic and potential. But temperature is decided only by the average kinetic energy of the molecules. All right. Now, the larger quantity will have a smaller increase in temperature, while the smaller quantity will have a larger increase in temperature. This is because more number of molecules share the additional energy in the big beaker, while in the case of the smaller quantity, less number of molecules share the same increase. That means the share of the energy per molecule will be larger in the small beaker. So look at the way I'm going to define temperature. Temperature of an object is proportional to the average kinetic energy of its molecules. Average kinetic energy per molecule is a measure of the temperature. Now, here I have another illustration. Suppose I have two objects. One object, you have this is a measure of the average kinetic energy, and this is the total potential energy of the molecules. In the second object, this is the measure of average kinetic energy, and this is a measure of the total potential energy. Now you notice here that the average kinetic energy is the same in both cases, and therefore the temperature is the same in both cases. But the internal energy is much greater in the second case because there is a greater amount of potential energy. You see, the temperature is determined only by the kinetic energy. And you remember this formula. Kinetic energy is 1/2 mv squared. Kinetic energy of a molecule is 1/2 mv squared, where m is the mass of the molecule and v is the speed of motion of the molecule. So I hope the distinction between temperature and internal energy is now fairly clear to you. Let's now talk about measuring temperature. How do we measure temperature? In order to measure temperature, we make use of properties of materials that change with temperature. Now, what does that mean? Now, if I heat an object like this, you know that it will expand. If I take some water in a test tube and heat it, you can see the volume of that water will increase. You can actually use that property to measure temperature. For example, most substances expand when heated, and the increase in volume is very nearly proportional to the change in temperature. And therefore, if you heat an object, you can use the increase in volume as a measure of the increase in temperature. And that is how we construct thermometers. Now, therefore, an increase in volume of a substance can be used to measure temperature. Now, have you seen a thermometer? A thermometer actually uses this property. If you take mercury or alcohol in a glass tube, you can see mercury or alcohol in glass can be actually used to construct a thermometer. Now, here is an example of a thermometer. I have a thermometer in my hand. Well, I don't think you can see much of it. Now, a thermometer has a bulb. Now, what I'm pointing now is the bulb. Now, this is an alcohol thermometer. It contains a colored alcohol, and the thermometer inside, the liquid inside, goes into a tube, and the level, I'm going to bring it closer to the camera so that you can have a look at it. Now, all right, can you see the red color? Now, that is the mercury inside the bulb. This is the bulb, and the mercury, not mercury, alcohol. The alcohol is rising inside. Can you see the level of mercury in the tube? Up to where is it? Let me see if we can actually see that. Yes. Isn't it up to here? There. That is the level of mercury now. Now, I'm going to put this thermometer in some warm water and see if you can watch if you can see the level increasing. All right. Now, let's see if you can actually watch that level. Can you see the level? Now, watch the level now if you can. Oh, well. Well, we didn't see much of the increase, did you? Well, the height of the mercury has actually gone up considerably inside the tube. In other words, when you heat the alcohol, its volume increases and it rises uniformly into that small tube. And you can make markings on the thermometer there so that you can use it as a thermometer. And that is how a thermometer is actually made. So here you have a mercury thermometer, and this is an alcohol thermometer. When you put the thermometer, the bulb inside a hot bath, for example, the level of mercury will rise, and the increase in volume is proportional to the increase in temperature. Therefore, you can use it to measure temperature. Now, in order to measure temperature, we need to use a temperature scale. Now, what is the common temperature scale that is used? Well, internationally, it is the Celsius scale. There are two main scales of temperature used in measuring temperature. One is called the Celsius scale, which uses the arbitrary temperature, namely the temperature at which ice melts as it's 0. So if you want to mark this thermometer using Celsius, what you need to do is put this thermometer in melting ice and mark the level of the mercury and call that 0 degrees Celsius. Now, put this inside melting ice and mark the level, that will be 0 degrees Celsius. The other scale is called the Kelvin scale. I know most of you want me to talk about Fahrenheit. I will not, because Fahrenheit is used only in America, and it's high time that we throw it away. We need to get in line with the rest of the world. Everywhere else it is Celsius, and scientific community uses the Kelvin scale. Now, what is the relation between Kelvin? What is the 0 in Kelvin? Now, that uses temperature at which the molecular energy is absolutely 0. So when you talk about the 0 in a Kelvin scale, it is the temperature at which the molecule of a substance has no energy at all. It is just quiet. And that is a very, very low temperature. Now, 0 Kelvin is a very low temperature. You got to go down to here, and that is 0 Kelvin. Actually, 0 Kelvin is about negative 273 degrees Celsius. That is the temperature at which the molecules of a substance will be absolutely quiet. No energy at all. Now, in the Celsius scale, the temperature is measured in a unit called degrees Celsius. We say the temperature is 20 degrees Celsius, the temperature is 50 degrees Celsius, and so on. Whereas when we use Kelvin, we will simply say so many Kelvin is the temperature. We will not use the term degree. In other words, 100 Kelvin, 200 Kelvin, 500 Kelvin is a measure of the temperature in Kelvin scale. Whereas in Celsius we say degree Celsius. Now, we use lowercase t to represent temperature in Celsius and uppercase T to represent temperature in Kelvin scale. And there is a fixed relationship between temperature in Kelvin and temperature in degrees Celsius, and that relation is, if you add 273, forget about that 0.15, if you add 273 to the temperature measured in degrees Celsius, you will get temperature in Kelvin. That is the relationship. So, this 0 degrees Celsius therefore is 273 Kelvin. and 100 degrees Celsius, that is the temperature at which water boils. In Kelvin, it will be 373 kelvins. All right, I'm ignoring that decimal part. So a relation between temperature in degrees Celsius and temperature in Kelvin, it is good to know that. Well, let's now talk about measuring heat. So far we talked about measuring temperature. Now we talk about measuring heat. Now, since heat is a form of energy, well, what is the unit for measuring energy? Energy is measured in joule. Therefore, heat, which is a form of energy, will also be measured in joules. Now, a unit called calorie was used in the past to measure heat. I'm sure some of you have heard about a calorie. 1 calorie is the amount of heat that will raise the temperature of 1 gram of water by 1 degree Celsius. So if I have some water here. If I take 1 gram of water, you know 1 gram of water is a very small amount. And if I want to increase its temperature by 1 degree Celsius, the amount of energy, the amount of heat I need to give is called a calorie. So the definition of a calorie: 1 calorie is the amount of heat that will raise the temperature of 1 gram of water by 1 degree Celsius. And 1 calorie is approximately 4.2 joules. That means if you supply 1 gram of water with 4.2 joules of energy, its temperature will increase by 1 degree Celsius. Alright? And 1,000 calories is called a kilocalorie. We write it kcal, a kilocalorie. Now, 1 kilocalorie is the amount of heat energy that will raise the temperature of 1 kilogram of water by 1 degree Celsius. You see, you know that 1 kilogram contains 1,000 grams. Is that right? So a kilocalorie, 1 calorie is the amount of heat you need to increase the temperature of 1 gram of water by 1 degree Celsius. And therefore, the amount of heat you need to increase the temperature of 1,000 grams of water. 1,000 grams of water is 1 kilogram. By 1 degree Celsius is 1 kilocalorie. Can you tell me how many joules is a kilocalorie? A kilocalorie is 4,200 joules, because 1 calorie is 4.2 joules. A kilocalorie means multiply that by 1,000, 4,200 joules. Now, the amount of energy released by the oxidation of the food you eat is also measured in calories. You see, there is something called food calories. I'm sure everybody knows that, because if you look at a food label, it is all given in calories. Alright, you look at your breakfast cereal, it says 1 serving is 60 calories. Now, is that calorie the same as this calorie? Well, no. 1 food calorie is the same as a kilocalorie. That's right. So 1 food calorie is a kilocalorie, that is 4,200 joules. That means 1 food calorie is the amount of heat that will raise the temperature of 1 kilogram of water by 1 degree Celsius. That is a kilocalorie, and that is called a food calorie. So remember, a food calorie is a lot of energy. So don't pile up a lot of energy. That will be very bad for you. Alright, so a food calorie is 4,200 joules. Now the label on a cereal packet read like this: 60 calories per serving. Now tell me, how many joules of energy are contained in one serving of the cereal? 60 calories. Each food calorie contains 4,200 joules. Therefore, how many joules are there in 60 calories? One food calorie is 4,200 joules. Therefore, 60 food calories is 60 times 4,200. That is 252,000 joules of energy. When you eat that breakfast cereal that is labeled 60 calories per serving, when you eat one serving, you know, one serving is not a large quantity. A lot of people eat 2 or 3 servings at the same time. You can imagine the amount of energy that food will give you. Now let me ask you this. Using this amount of heat, to what temperature can 1 kilogram of water be raised if the initial temperature of water is 20 degrees Celsius? Remember, in order to raise the temperature of 1 kilogram of water by 1 degree Celsius, you need 4,200 joules. Therefore, using this much of heat, how many degrees Celsius can you heat 1 kilogram of water? Well, 60 calories is 60 kilocalories, and 1 kilocalorie raises the temperature of 1 kilogram of water by 1 degree Celsius. Is that right? 1 kilocalorie, that is 4,200 joules, will raise the temperature of 1 kilogram by 1 degree. Therefore, 60 kilocalories will raise the temperature of 1 kilogram by 60 degrees. So, 60 kilocalories will raise the temperature of 1 kilogram of water by 60 degrees. So, if the initial temperature is 20 degrees Celsius, the final temperature of that water will be 80 degrees Celsius. You see that? By one serving of your cereal, you can actually take 1 kilogram. Now here, if I fill this beaker with water, that will be 1 kilogram of water. I can heat this water to 80 degrees Celsius. I can almost boil it with the energy contained in one serving of cereal. So you can see food that we eat contain large amounts of energies. Now you need to burn that energy off by working hard or doing exercise. Otherwise, this energy has a tendency to store, increasing your body weight. You can see I have very little of that. Alright, there's a challenge for you. And this challenge, I'm going to give you 3 extra credit points if you can do this. 3 extra credit points. An average person's food intake is about 2,000 food calories. Remember when I write the big C is used for a food calorie. So the average person's food intake is about 2,000 food calories. Use reasonable assumptions to find the number of kilograms of water that can be boiled using this energy. Alright, I want to see if anybody wants to take up that challenge. That challenge is worth 3 extra credit points. Alright, so as soon as you do that, send it to me. Write all the steps. Don't just give it to me one line answer. I want to see all the steps you have. In other words, you can start like this. 1 kilojoules raises the temperature of 1 kilogram by 1 degrees. And therefore, remember, each food calorie is a kilocalorie. So 2000 food calories will increase the temperature. So give it to me step by step like that. Alright, let's now go and talk about another concept called specific heat of a substance. Specific heat of a substance. What does that mean? Specific heat of a substance is the amount of heat needed to raise the temperature of 1 kilogram of a substance by 1 Kelvin. Now, I have been using this object in many of my demonstrations. Do you remember what this is? I showed you in my first class. This is a mass of 1 kilogram and this is made of brass. Now, if I want to increase the temperature of this 1 kilogram of brass by 1 degree Celsius, I need to supply a certain amount of heat. That amount of heat I need to supply to this to increase its temperature by 1 degree Celsius is called the specific heat of this substance of brass. Specific heat of a substance is the amount of heat needed to raise the temperature of 1 kilogram of the substance by 1 Kelvin. Now remember, raising the temperature by 1 Kelvin and raising it by 1 degree Celsius are exactly the same, because the temperature difference in Celsius and Kelvin are the same. The only way they differ are the beginning at where they start. Otherwise, their temperature differences are both the same. Okay. In that case, can you tell me what is the specific heat of water? What is the amount of heat I need to raise the temperature of 1 kilogram of water by 1 degree Celsius or 1 Kelvin? We talked about this. We said 4,200 joules of energy are needed to increase the temperature of 1 kilogram of water by 1 degree Celsius. Therefore, the specific heat of water is 4,200 joules per kilogram per Kelvin. So, specific heat is measured in a unit. Look at this. The amount of heat needed to raise the temperature of 1 kilogram by 1 Kelvin. Joules per kilogram per Kelvin. And we represent specific heat by the lowercase c. 4,200 joules of heat is required to raise the temperature of 1 kilogram of water by 1 Kelvin. So if I have 1 kilogram of water here, I need to give 4,200 joules of energy to it so that its temperature will increase by 1 degree Celsius or 1 Kelvin. And therefore, specific heat of water is 4,200 joules per kilogram per Kelvin. On the other hand, you need only 390 joules of heat to raise the temperature of 1 kilogram of copper by 1 degree Celsius or 1 Kelvin. So 1 kilogram of copper requires only 390 joules to raise its temperature by 1 Kelvin. So what is the specific heat of copper? The specific heat of copper is 390 joules per kilogram per Kelvin. Alright. The quantity of heat Q required to raise the temperature of m kilogram of a substance from an initial temperature theta 1 to a final temperature theta 2. Well, let me ask you this. If I need 4,200 joules of energy to increase the temperature of 1 kilogram of water by 1 Kelvin, how much heat I need to increase the temperature of 2 kilograms? It will be 2 times 4,200, right? Alright, instead of increasing the temperature through 1 Kelvin, if I increase it by 5 Kelvin, I need then 5 times that amount of heat. So, now tell me, if you know the specific heat of a substance, how do you calculate the amount of heat that is needed to raise the temperature of m kilogram of a substance from an initial temperature theta 1 to a final temperature theta 2? Now this is the formula, and I want you to take note of that. The quantity of heat that you need to supply to m kilogram of a substance to increase its temperature by delta theta. What does delta theta stands for? The change in temperature. In here, it will be theta 2 minus theta 1. Delta theta is the change in temperature. M is the mass of the object. C is the specific heat of the substance. And delta theta is the change in temperature. So what does MC delta theta give you? It's a measure of the quantity of heat required to raise the temperature of m kilogram of a substance by a temperature difference of delta theta. So delta theta is theta 2 minus theta 1. If I have a quantity of water m kilogram, in order to change its temperature by delta theta, the quantity of heat I need to supply is mass times specific heat times change in temperature. Now, I'm going to give you specific heat values of some common substances. The specific heat for aluminum is 900 joules per kilogram per Kelvin. In other words, 900 joules of heat energy are required to increase 1 kilogram of aluminum. I'm holding an aluminum actually here. To increase the temperature of 1 kilogram of aluminum by 1 Kelvin, you need 900 joules of heat. For alcohol, that value is 2400. For copper, it is 390. So I have a number of substances and their specific heat. Water at room temperature is 4200, and the specific heat of ice is 2050. Alright, we might use this, so keep a note of this in your book. Let's now talk about latent heat and change of state. Now, when I talked about the different states of matter, I told you in order to change a solid to a liquid, you need to increase the potential energy of the molecules. Now, an increase in potential energy does not change the temperature of the substance. Therefore, during the time when a solid melts to become a liquid, the additional heat supplied to do that will not result in an increase in temperature. And therefore, such a heat is called a latent heat. Latent means hidden. Now, you cannot measure it by measuring the temperature. When heat is supplied to a solid, the kinetic energy of its molecules increase, and hence the temperature of the solid will increase. Is that right? The molecules will begin to vibrate faster and faster, faster and faster, until the temperature reaches the melting point. Now, this continues until the solid reaches its melting point. Now, once the temperature reaches its melting point, when you supply additional heat, that additional heat will not increase the temperature of the solid. So what is that additional heat used now? The additional heat is used in breaking the molecular bonds so that the molecules can free themselves to change into the liquid form. You see that? The potential energy of the molecules increase, and that will not increase the temperature. So the additional heat added does not increase the kinetic energy of the molecules. Instead, it is used to overcome the intermolecular forces holding the molecules together so that they are free to move about. You see, that amount of heat you supply will not result in an increase in temperature. So this is the time when a solid turns into a liquid. Now during this change of state, the molecules do not speed up. During the time they change from solid to a liquid, the molecules don't speed up. They simply get separated. The potential energy increases. There is gain in potential energy. There is no temperature change. You see, as you supply heat, what happens? The kinetic energy increases, and at the melting point, the extra energy is used in freeing the molecules from one another so that the molecules are now free to move about. Now, when heat is supplied to a liquid, now once the solid is melted to a liquid, now you supply heat, the molecules will begin to increase its kinetic energy. So when heat is supplied to a liquid, the translational kinetic energy of its molecules will increase and the temperature of the liquid will increase. Now, this continues until the liquid reaches its boiling point. So the increase in kinetic energy continues only until the liquid reaches its boiling point. Now, when the liquid reaches its boiling point, any additional heat added does not increase the kinetic energy of the molecules anymore. Now, what is that additional heat now used? To free the molecules from one another. That means that additional heat supplied will now supply potential energy to the molecules so that they are free to move away from each other. When the liquid is at its boiling point, the additional heat required is simply used to break the molecules away from each other so that they can now move about. Now this is the time a liquid turns into a gas. So let me summarize this once again. When a solid is heated, the amount of at the melting point, the molecules do not gain kinetic energy anymore. The extra energy supplied will increase the potential energy. So during a change of state, when solid changes to a liquid, the additional heat supplied will not increase the temperature. It increases the potential energy of the molecules. And now, once all the molecules have now become liquid, when you supply heat, that molecules will begin to move faster and faster until the liquid reaches the boiling point. At the boiling point, you supply additional heat. What happens? That will not increase the kinetic energy of the molecules anymore. The additional heat is used to separate the molecules from one another, giving molecules potential energy. Length and so, when a solid melts to become a liquid, the latent heat is absorbed. The same way, when a liquid evaporates or boils to become a vapor or a gas, latent heat is absorbed. Now tell me, if a vapor or a gas condenses back to liquid, now in order to do that, the molecules have to give up their potential energy. You see, from a liquid to gas, to change a liquid to a gas, we give the molecules the additional potential energy needed to break away from each other. If you now want to bring these molecules back to liquid, this is the process called condensation. Now, when a gas condenses to become a liquid, the molecules have to give up their additional potential energy. In other words, the latent heat that time is released to the surroundings. In the same way, a liquid now solidifies. When a liquid forms a solid, the extra potential energy is released. So when a vapor condenses back to liquid, heat energy is given out, but it does not lower the temperature. That heat given out will not lower the temperature. That heat given out is a measure of the extra potential energy the molecules had. Remember, temperature is determined only by the kinetic energy. Now, since the amount of heat absorbed or liberated, that means a heat is absorbed when a solid becomes a liquid. The heat is liberated when a liquid becomes a solid. Similarly, heat is absorbed when a liquid becomes a vapor and liberated when a vapor becomes a liquid. So, I'm going to use that term. Since the amount of heat absorbed or liberated during a change of state does not manifest in a change in temperature, this heat that is absorbed or liberated during a change of state due to the changes in the potential energy is called the latent or hidden heat. Now, we use uppercase L to represent latent heat, and it is measured in joules per kilogram. Remember, there is no change in temperature. It is the amount of energy either absorbed or liberated for 1 kilogram of the substance to change its state. Joules per kilogram. Now, I'm going to define the latent heat. Specific latent heat of fusion of a substance is a measure of the amount of heat absorbed or liberated by 1 kilogram of that substance at its melting point to convert either from solid to liquid or from liquid to solid without a change in temperature. Now remember, during a change of state, there is no temperature change. So when we talk about latent heat does not constitute a change in temperature. So we use L sub F to represent the latent heat of fusion, and it is measured in joules per kilogram. Now look at the latent heat of fusion of water. LF is 333.5 kilojoules per kilogram. You need 333,000 joules in order to convert 1 kilogram of water, of ice to water, or 1 kilogram of water when turning to ice, it will release that much amount of heat. That's a tremendous amount of heat. Now let's define a latent heat of vaporization. There are two types of latent heats, is that right? One involves change from a solid to a liquid or backward, liquid to solid. The other involves from liquid to vapor or from vapor to liquid. And that is called the latent heat of vaporization. So specific latent heat of vaporization denoted by L sub V of a substance is a measure of the amount of heat absorbed or liberated by 1 kilogram of a substance at its boiling point to convert either from liquid to vapor or from vapor to liquid without causing a change in temperature. And for water, it is 2,257 kilojoules per kilogram. It's a tremendous amount of heat, and that is the reason why we have so much amount of water left on the earth. if the latent heat of vaporization were a small quantity, all the water would have become vapor long time ago. You see how lucky we are that water has a very high latent heat of vaporization, so that we have lots of water around. The amount of heat Q required to convert m kilogram of a solid at its melting point to liquid at the same temperature is Q equal to m times LF. Remember, LF is the amount of heat needed to convert 1 kilogram of solid either from solid to liquid or from liquid to solid. And if you want to therefore convert m kilogram, the total amount of heat will be m times LF. Similarly, the amount of heat Q required to convert m kilogram of a liquid at its boiling point to vapor at the same temperature, can you tell me what that will be? That will be Q equal to mL sub V, latent heat of vaporization. Now, these two formulae I want you to remember. Now, we did another formula when we talked about specific heat. That means specific heat involves a change in temperature, whereas latent heat of fusion or latent heat of vaporization does not include a change in temperature. You see, when there is a change in temperature, it is the specific heat that is involved. And in order to change the temperature of a substance, the quantity of heat is mass times specific heat times the change in temperature. This is the formula we used to calculate the quantity of heat that is required to change the temperature of a substance. You see, the quantity of heat required to change the temperature of a substance is mass times specific heat times change in temperature. Whereas the quantity of heat required to change m kilogram of a solid to liquid without a change in temperature is mass times latent heat of fusion. And the quantity of heat required to change 1 kilogram of a liquid to vapor at the same temperature is mass times latent heat of vaporization. Okay. Let me now give you some values of latent heat of fusion and latent heat of vaporization of some common substances. Now, the melting point of alcohol is 159 Kelvin. Now remember, 159 Kelvin is below 0 degrees Celsius, because 0 degrees Celsius is 273 Kelvin. Now, the latent heat of fusion is 1.04 times 10 to the 5 joules per kilogram. And the latent heat of vaporization is 8.5 times 10 to the 5. And we will only use this for water. You can see the melting point for water is 0 degrees Celsius, 273 Kelvin. The latent heat of fusion is 3.34 times 10 to the 5 joules per kilogram, and the latent heat of vaporization of water is 2.26 times 10 to the 6 joules per kilogram. Alright, we will need these values to solve small problems. Okay, the state of a substance can be changed by supplying or removing sufficient quantities of heat. So by our discussion so far, now you know the state of a substance, solid, liquid or vapor, can be changed by either supplying additional heat or by removing heat from the substance. Now, I'm going to give you a summary of the phase change. What is the meaning of phase change? A substance changing from solid to a liquid is a phase change. A liquid changing from liquid state to vapor state is a phase change. A vapor condensing back to liquid is a phase change, and so on. Now, what is the name for that phase change? How about the heat movement? Is heat absorbed or liberated? And is there any temperature change during the phase change? Now, what is the answer for that last question? Is there any temperature change during a phase change? No. During a phase change, when a substance changes from one state to another, there will be no temperature change. All right. That's the first one is solid to liquid. A change from solid to liquid is called melting. And what is the heat movement? Heat goes into the solid to melt it. In other words, solid absorbs heat so that it melts. And there is no temperature change during that phase change. So you must be familiar with these terms. Liquid to solid. What do you call that phase change? What is the name for that? A liquid changes to a solid. It's called freezing. A liquid freezes to become a solid. What is the movement of heat? Heat goes from where? Well, liquid will lose heat. Liquid throws away heat. Heat leaves the liquid during that phase. And is there any temperature change? No. All right, let's go to the next one. Liquid to gas. What is the name used for that? A liquid to gas is called vaporization. Now, what is the heat movement? A liquid will absorb heat during that change. So heat goes into liquid. Is there any change in temperature? No, there is no change in temperature. Alright, what is the name given to this change? A gas to a liquid. A vapor condenses to become a liquid. It's called condensation. Alright, condensation, what is the heat flow? Heat leaves the gas. When a vapor condenses to become a liquid, heat is liberated. Heat escapes to the surroundings. Is there a temperature change? No, there is no temperature change. How about, have you seen a solid directly changing to a gas? Yes, if you open your freezer compartment, you can see water vapor, a lot of water vapor there, right? Ice goes directly into vapor. Now, that process, when a solid goes directly into a gaseous state, the process is called sublimation. I want you to remember that one. The process by which a solid goes directly to a gas is called sublimation. Well, carbon dioxide, have you seen dry ice? What you call a dry ice is frozen carbon dioxide. It doesn't go through the liquid state. It can be frozen directly to a solid. Now, heat goes into the solid during sublimation, and there is no temperature change. During a phase change, there is no temperature change. All right, I'm going to take an example to illustrate what we said so far by taking 1 kilogram of ice at minus 50 degrees Celsius. All right, I'm going to take 1 kilogram of ice at minus 50 degrees Celsius, and I'm going to supply heat to that. And let's trace out what are the changes that happen. All right, as heat is supplied to this ice at minus 50 degrees Celsius, what will happen? The temperature will steadily increase. Increase up to what? Increases until it reaches 0 degrees Celsius. Can you tell me what is the increase in temperature. What is the increase in temperature? When 1 kilogram of ice is heated so that its temperature increases from negative 50 degrees to 0 degrees. You see, look at the equation we are going to use. I'm going to call that quantity of heat Q1. And when there is a change in temperature, it is this equation, mc delta theta, mass multiplied by specific heat multiplied by change in temperature. Alright, I'm going to put all these things on a graph. We are starting here, ice at negative 50 degrees Celsius. Now, if you look at this, let's give the values. The mass is 1 kilogram. If you remember the specific heat of ice, I gave it to you in a table, 2050 joules per kilogram per Kelvin. And the change in temperature, what is the change in temperature? The temperature changes from negative 50 degrees to 0 degrees. The change in temperature is 50 Kelvin. And when you multiply this, you get this 1.03 times 10 to the 5 joules. So the ice, we started here, ice at negative 50 degrees Celsius. You supplied heat to it so that its temperature became 0 degrees Celsius. There you are. So the ice at negative 50 degrees absorbs this much of heat so that its temperature now is 0 degrees Celsius. The amount of heat that you supplied is 1.03 times 10 to the 5. That is the amount of heat absorbed by ice for that change in temperature. Alright, now tell me, I'm going to supply more heat to my ice. What happens? Now, because ice is now at 0 degrees Celsius, additional heat supplied will not increase the temperature. But what is going to happen? Ice is now going to melt to become water. A phase change is going to happen. Now, heat is absorbed, but that absorbed heat will not cause a change in temperature. Alright. As further heat is supplied, ice at 0 degrees changes to water at 0 degrees. There is no change in temperature. Can you tell me what is the equation for the amount of heat absorbed by ice at that time? I'm going to call it Q2. The amount of heat absorbed during that time is mass multiplied by latent heat of fusion. Now, mass of water of the ice is 1 kilogram, and latent heat of fusion, I gave it to you in a table, 3.34 times 10 to the 5 joules. Now, that will be 3.34 times 10 to the 5 joules. Now, that happens when ice becomes water. You can see there will be no temperature change. Look at the horizontal line. There is no temperature change. All of the substance is ice here where I'm pointing. And all that ice is now water here. And the temperature here and the temperature here are the same. The temperature has not changed. All this amount of heat is used for that phase change. Change the ice to water. So this is Q2, which is 3.34 times 10 to the 5. Now tell me, I'm going to supply now more heat. What's going to happen? Now if you supply more heat, all the ice has now become water. Now water molecules are going to move faster. The temperature of water is going to increase. So, once all the ice is melted, the temperature rises until it reaches the boiling point of 100 degrees Celsius. So once all the ice is melted, the additional heat you supply is now used to increase the kinetic energy of the molecules. The temperature will increase. Now, can you write an equation for the amount of heat absorbed by water at that time? Now it is water, no more ice. And that will be Q3. I'm going to call that Q3. Is mass times specific heat of water times the change in temperature. Alright, tell me, what are these values now? What is our mass? Mass is 1 kilogram. What is the specific heat of water? Do you remember? That is 4,200 joules per kilogram per Kelvin. And what is going to be our change in temperature? Our water is going to increase its temperature from 0 to 100 degrees Celsius. So that delta theta, the change in temperature, is 100 degrees Celsius. So that is 1 kilogram times 4,200 joules per kilogram per Kelvin times 100 Kelvin. And that is 4.2 times 10 to the 5 joules. So absorbing this amount of heat, water at this point is going to increase its temperature to 100 degrees Celsius. That's 100 degrees Celsius. Now, the amount of heat supplied is Q3, and that is equal to 4.2 times 10 to the 5. Now, that water is at 100 degrees Celsius. Okay, we are supplying heat now. What happens to the amount of heat absorbed by water? Now the temperature will not increase any further. The additional heat absorbed by water is now used to increase the potential energy of the molecules, to change the state from liquid to vapor. Alright? As further heat is supplied, water at 100 degrees Celsius changes to steam at the same temperature without changing in temperature. So the quantity of heat Q4 this time is mass multiplied by latent heat. Now remember, there is no change in temperature here. What is our mass? Mass is 1 kilogram. What is latent heat of vaporization of water? Do you remember? It is 2.26 times 10 to the 6 joules per kilogram. And that gives me 2.26 times 10 to the 6 joules is the amount of heat that is used by this water to change into steam. There you are. So at this point where I'm pointing, all of the substance is water. And the heat absorbed now gradually converts all of it to steam here. So all of the substance is now steam. How much energy? Is 2.26 times 10 to the 6. You can see what we did. We took a block of ice of 1 kilogram from negative 50 degrees and continuously supplied heat so that its temperature increased. Then all the ice melted to become water, no temperature change. And then the water started increasing in temperature, and then all that water became steam. And look at the total amount of heat that you need to supply. If you add all these, that is the total measure of the heat that you supplied. Okay, so the total heat absorbed will be Q1 plus Q2 plus Q3 plus Q4, and that will be, add all these. If you got a calculator, you can put it and add. I got this 3.12 times 10 to the 6th. I would like you to test if this number is correct. Try and add all these numbers and see whether you get this. Okay? Alright, let's do a very small problem. How much heat is absorbed by 2.5 kilogram of copper when heated from 20 degrees Celsius to 60 degrees Celsius? Now the first thing you notice here, there is a change in temperature. So the quantity we use here is the specific heat, not the latent heat. When there is a temperature change, we use the specific heat. When there is no temperature change, we use the latent heat. Alright, do you remember the specific heat formula? The quantity of heat required to change the temperature of a substance. It is mc delta theta. Is that right? Alright, we got the mass of copper is 2.5 kilogram. The specific heat of copper, if you remember the table I gave you, is 390 joules per kilogram per Kelvin. And delta theta, the change in temperature, it is heated from 20 degrees Celsius to 60 degrees Celsius. The change in temperature is 60 minus 20, that is 40 degrees Celsius. And therefore the quantity of heat, now look at, I depend on my computer to correct my spelling. Now I wanted to write heat and it became meat, and the computer did not correct me. So read it as the quantity of heat absorbed is, what is the formula for quantity of heat absorbed? Q equal to mc delta theta. Mass we know, specific heat we know, the change in temperature we know. So using those values we get Q equal to 39,000 joules of heat is absorbed in that process. Okay? Another one. How much heat is liberated when 10 grams of steam condenses to form water? Now tell me, is the process here, is the process that involves specific heat or latent heat in this case? The question is, how much heat is liberated when 10 grams of steam condenses to water? Now, does this process involve specific heat or does it involve latent heat? Well, this is a phase change, a change from one state to another. Therefore, what is involved is latent heat. There is no temperature change here. You see, specific heat is involved only when there is a temperature change. This does not involve a temperature change. 10 grams of steam at 100 degrees Celsius simply condenses to form water at the same temperature. There is no temperature change. Alright, now what is the formula for amount of heat during a change of state? Q equal to mass times latent heat. Is that right? And in this case, the latent heat is of vaporization. Alright, the mass is 10 grams, but you need to write that in kilogram. 10 grams is 0.01 kilogram. Latent heat of vaporization of water is 2.26 times 10 to the 6 joules per kilogram. I gave it to you early. And therefore, what is the amount of heat that is liberated? You know that when vapor condenses to form liquid, heat is liberated. What is the amount of heat liberated? Since there is no change in temperature, the quantity of heat liberated is Q equal to mass times latent heat of vaporization. Now, mass is 0.01 kilogram. Latent heat of vaporization is 2.26 times 10 to the 6th. And therefore, that quantity of heat is 2.26 times 10 to the 4 joules. Well, I want you to review what we did today. Alright? Now, we talked about some very important concepts. I want you to be very sure about it. So, after watching the lecture, look through the PowerPoint and do your homework. Very important. I have given you a number of homeworks and I have worked them out for you. So go through the homework and learn all these. I'm going to use a second part of this lesson later on. So I will see you for the second part later on.